briefly introduce you, Andrea. So Andrea, Dr. Gabrieli, is an interesting person with a very varied background. He has a degree in physics from Italy, University of Milan, one of the big universities in Italy. He's worked on seismology and then moved to the UK, working on a master's degree in volcanology and geological hazards with Lionel Wilson. And since most of you are not geologists or even volcanologists, you probably haven't heard that name, but Lionel Wilson is really royalty in volcanology and in geological hazards. So this is the best pedigree you could wish for in that field. He worked on triggers for volcanic eruptions, had a Best Dissertation Award, and then went on to do a PhD at the University of Hawaii at Manoa. And he liked it so much that he stayed on. I can't blame you, Andrea. It's a great place to live, and maybe not the cheapest in the world. And he worked with Rob Wright there. Robert Wright is currently the director of HIGP. That's the institute there with multiple faculty working on geological hazards and oceanography and planetary science. He's a remote sensing expert, Andrea is, and he's currently as postdoc and affiliate faculty member at the institute, working with Rob on the Hyperspectral Thermal Imager. That's an ESTO tech demonstration that will launch soon, and also on self-driving vehicle research. So it's really interesting, and he will tell us a little bit about trace gases from volcanoes and thermal hotspot detection. And Andrea, we have 17 on the line now, so it's getting more. And the floor is yours. Welcome.
Thank you very much, Florian. Thank you for the introduction, and thank you everyone for being here. So today we're going to talk about new methods that I've been working on as part of my PhD, and I'm still working on as part of my postdoc for rapid retrieval of atmospheric trace gases and thermal hotspot monitoring as well. So specifically, we're going to talk about 4 different projects. The first one, mapping land surface temperature and sampling volcanic sulfur dioxide using onboard computing as part of the HyTI mission. That's the one Florian was referring to during the introduction, the Hyperspectral Thermal Imager mission. Using carbon dioxide to determine inter-vehicle range for self-driving vehicles. We're also going to mention detecting low-intensity volcanic thermal emission from MODIS data, so kind of trying to detect the unrest before eruptions. And the last one I want to briefly mention is really a proposed work that I'd like to carry out with Florian and Matt, hopefully joining you guys at AIMS. So understanding how changes in volcanic signals measured from space reflect in transition in activity at at various volcanoes. So you see, the main theme of this talk is volcanic gases. So let's dive into it right now. Measuring volcanic gases is key because they convey information regarding magma movements about magma at depth. Many volcanic gases of interest that you see in this cartoon have distinctive spectral features. Here I'm showing you the thermal infrared. So here, for example, you see sulfur dioxide, carbon dioxide, ash, all very important. And hyperspectral thermal imager can detect these features at high spatial, spectral, and temporal resolutions with high signal-to-noise ratios. And during the first part of this talk, I'm going to mostly talk about 2 instruments, a ground-based hyperspectral imager called PHI, the thermal hyperspectral imager, which is a Sagnac-based device, which you can see here in this picture. And also I'll be referring to HyTI, the 6U CubeSat platform. It's the ESTO technology validation mission. So Peter Francis used to say that volcanic gases are like telegrams from the Earth's interior. And here I want to show you exactly what he meant by considering an example. Here you can see the solubility curve, a solubility curve of water, which is, you see there's pressure on the y-axis and the amount of volatile that is dissolved into a particular magma. The solubility curve means it is the limit pressure under which a particular volatile can be dissolved into magma. So you can see at high pressure. So let's consider, for example, for this example, 3 weight% water dissolved in rhyolite. And you can see the rhyolite, the piece of rhyolite here on the left. This is rhyolite kept in a special oven under high temperature and high pressure in a lab at Lancaster University. So you see, as the pressure, as magma rises, so in the simulation, the pressure decreases. Nothing really happens until you see the solubility curve is hit. You see the red line here represents magma ascending into a volcanic plumbing system. When the solubility curve is hit, that means we're reaching the limit pressure under which water, in this case, can be dissolved into the melt. If we go a little bit beyond the solubility curve, meaning the pressure decreases a little bit more, then what happens is that you can see it here, bubbles begins to form in the rhyolite. So the water begins to be exhaled from the silicate melt. The bubbles rise, driving the melt upwards faster and faster, ultimately leading to subaerial volcanic eruptions that you can see in this cartoon. Now there are a variety of volcanic volatiles dissolved into magmas. Here you can see a cartoon. There's an ideal volcano with a variety of volatiles. Volcanic sulfur dioxide, which you can see here, is widely used by volcanologists because of its ubiquitous presence in volcanic plumes. But this means that it's very easy to detect because there's not a lot of sulfur dioxide in the atmosphere. So its detection at a volcano can be immediately linked to magma being injected into the shallower magma reservoirs, and so be linked to volcanic activity. Problem is, you can see here I mentioned shallow reservoirs. In fact, this bar here represents the amount of volatiles being exhaled from the melt at a particular depth. The larger the band here, the more volatile is exhaled. You can see SO2 peaks, SO2 exhalution peaks at relatively shallow depth. This means that its detection doesn't provide early warnings for volcanic activity. There are other gases such as carbon dioxide, which whose exhalution peaks at greater depth. But the problem is that it's tougher to detect carbon dioxide because of its presence in the atmosphere. There's already a large signal in the atmosphere, so it's difficult to distinguish the volcanic signal from the atmospheric signal. Studying volcanic gases is also important for public health. This is true for all trace gases in the atmosphere as well. Here you can see a picture I took of an overflight of the Pu'o event at Kilauea. You can see sulfur dioxide clouds being degassed and carried away from the wind. Sulfur dioxide is particularly, it gets translated into sulfuric acids and aerosols because of sunlight in the atmosphere. So communities living downwind active volcanoes can be affected, by these gases, and so it should be monitored. Communities, people, plants, infrastructures, everything can be affected. So it's important to monitor these gases for these reasons. What here at the University of Hawaii we're proposing of doing is using this particular technology, the Hyperspectral Thermal Imager, to demonstrate high spectral, high spatial, high signal to noise, long wave infrared imaging on board a 6U CubeSat platform, as well high performance onboard data analysis. So here you can see the 3 pieces of technologies that we would like to validate as part of this mission. You can see our HIGP interferometer. It's a Fabry-Perot interferometer. So Here you can see two pictures of the actual interferometer. It consists of two pieces of germanium stick together at an angle with air in between to introduce the phase shift when light comes in. This that you can see here, it's a particular prototype that was originally developed under funding from NASA and DARPA. And HyTI will provide the 25 channels between 8 and 10.7 microns with a 60-meter sample distance on the ground. You can see also the JPL. This project is a large partnership. So there's JPL. We're going to validate in space for the first time their bird detector. And also we're going to validate the Unibap Deep Delphi small onboard computer here. What we're going to focus on this presentation is the onboard computing part. So what we're going to try and do is obtain to process the raw data to level 1 to level 2 all on board on this Unibap spacecraft. So how does HyTI acquire data? Well, you can see when light comes in, it gets focused by this refractive lens. Here is an image showing the inner parts of HyTI. Here you can see the lens. And then light goes directly into the Fabry-Perot interferometer, where it's modulated by the fringes of the interferometer. Here you can see a sample cartoon illustrating a volcanic plume acquired at time t. Well, one single image that you can see here doesn't give us any spectral information. It does not give us the temperature of the scene either, because this is just thermal energy modulated by the fringes of the interferometer. So, but an interferogram can be reconstructed by forward motion of the platform. So it's important, HyTI has no moving parts. So what happens is that as the spacecraft orbits on the Earth, the forward motion, every target on the ground is imaged as the platform moves forward. It is imaged at each of the optical path differences of the interferometer. So you can see the fringes basically are carried across or scanned across the image target on the ground. See, you can see here is the cartoon. Now what happens is that upon co-registration of these images, it is possible to obtain a data cube of basically different images acquired at each optical path differences. Now, by calibrating these images spectrally and radiometrically, it is possible to get temperature. And so you can see by drilling into the data cube for each pixel, it is possible to get an interferogram with temperature. And then by FFT, it is possible to obtain spectral information. Here you can see measure spectrum of SO2 versus a model 1. This is not HyTI data. This is STI, the ground-based sensor I briefly mentioned at the beginning, which works in a similar way, except that the interferometer is not Fabry-Perot, it's a standard one. This is raw data from level 1. Obviously, to go from level 1 to level 2, we can't perform a full radiative transfer retrieval on board for obvious, computational limitations. What we want to do instead is to develop a single point retrieval algorithm. So it's a pixel independent algorithm. And so you can see here, for example, one pixel of a volcanic plume imaged by HyTI at ISS orbit is a function of a variety of things: the atmospheric profiles, the viewing geometry, the plume conditions, the background conditions, whether there are clouds in the back of the plume or nearby. So it's a variety of conditions, and you can see this variability of the atmosphere really affects the retrieval. Here you can see spectra simulated using Matran. All of these spectra were simulated for a ground-based sensor at the summit of Kilauea volcano, looking at the SO2 plume with a path concentration of 7,000 parts per million meters. So all of these spectra were obtained using 7,000 ppm. But you see how the variability of the atmosphere impacts the retrieval. These are spectra, I'm using atmospheric soundings for a year of data, worth of data at the summit of Kilauea. There's no way we can simulate this, I mean, so many spectra and do a retrieval using, you know, best fitting algorithms on board. So what we're doing instead is to build a giant lookup table built with a sufficient number of spectra, and then train a partial least square regression algorithm. It's a kind of statistical method, very powerful, that can handle this kind of data. And the training is done by simply associating the SO2 path concentrations used to generate these synthetic spectra and mapping and associating them to each of the spectra obtained under each of the conditions contained in the lookup table. This is done by simply solving these equations, whereas the known SO2 is simply the vector multiplication by the various radiance terms by particular alpha coefficients, whereas alpha coefficients are vectors. What's in the vectors? Well, in the vectors are the number of components of the models. How many components can we select? Well, here is a cartoon that illustrates, sorry, this is not a cartoon, this is a real graph, illustrating the percent variance explained in the output over the number of PLSR components. Let's say, for example, we're considering a 40 degrees elevation angle, again, ground-based sensor at the summit of Kilauea. 3 components explain 95% of the variance. If we go to 5, we can get even close to 100. And so you can see this is a one-on-one best fit showing the theoretical performance of the model. You can see 2 components, the fit is like this, 5 components is a little better. It's important not to overfit the model with noise by not selecting too many components. So here is the cool part about this. Once this training is done, the retrieval algorithm is simply done by carrying out this vector multiplication. So simply multiplying the radiance measured by the alpha coefficients. Here you can see a real measured spectrum of SO2 gas. You can see the nice SO2 emission feature at 8.6 microns. This is just ozone. And so the retrieval is done by a simple vector multiplication without using the giant lookup table anymore. So this is where, this is why it's possible to use this retrieval with a limited number of floating point operations per pixel. We call this retrieval ALTA, which in Spanish and Italian means high, so the high gas, basically. And so it's the amenable lookup table algorithm, because it's an amenable way of carrying out a complex inversion. We tested this retrieval extensively on the ground using, again, this sensor called HyTI. It's kind of a HyTI older brother. You can see we filled a gas cell with known amounts of SO2 representative of those found in volcanic plumes, and stick it in front of the sensor and imaged across a variety of backgrounds, such as clear sky, for example, or cloudy sky. We also used a variety of materials. And you can see this is how we retrieved the actual SO2 concentrations. We knew this because we filled the gas cells, and how we retrieved it using ALTA. You can see the one-on-one fit is quite well here. It's a little poorer when we have clouds in the background, but that's because the thermal contrast between the temperature of the gas and the temperature of the background was poor. So that's important always to keep in mind the temperature contrast here. We also tested this retrieval algorithm on the Big Island using Kilauea volcano at night and during daytime. You can see here 2 pictures of Thai standing on the summit of Kilauea. And here you can see some results. This is on the left, you can see a daytime retrieval of an SO2 gas plume. And on the left side, at nighttime, a retrieval with clouds in the back. You can see we had low altitude clouds rolling in from the east. so from the windward side of Big Island. And so you can see we were able to discriminate the plume quite well. We determined the sensitivity using well-calibrated, well-constrained laboratory experiments using the gas cells. You can see 1000 ppm for daytime, about 100 ppm for nighttime. We obtain a variety of these images, and then by summing each line, so by drawing basically a closed line over the vent and summing each line, the amount of SO2, and multiplying by the wind speed, which can be derived exactly directly from the hyperspectral image cube tracking the plume motion, we were able to obtain flux information. So you can see here, about 2 hours worth of flux data obtained in February 2018. We smoothed the data. We were able to capture some low transitions from low gas to high gas emissions at Kilauea, and we compared these to seismic data thanks to Matt Patrick at USGS, who gave us the data. And you can see the agreement is quite well. It works quite well because we were able, the increase of gas which we were able to detect is also can also be seen in the seismic noise. So meaning the lava lake became more active here. Now back to the fun part. Obviously we don't have any HyTI data yet, but we trained an ALTA algorithm for HyTI and tested it on master data. So master is the MoDisaster airborne simulator, about 10 channels in the thermal infrared. And here you can see a very interesting retrieval. We retrieved an image of master from Kilauea when this is part of the HISPIRI campaign over Kilauea. This is in January 2018. We retrieved the volcanic plume. You can see the different concentrations here. And then we got this data processed using Vince Reamuto's full retrieval at JPL. You can see the agreement is quite well. If you look at all the different features that I'm pointing here with the arrow, the agreement works quite well. So this is a very simple retrieval which carries out about 100 floating point operations per pixel, as opposed to a full full radius transfer retrieval. So agreement here is good. HyTI is not only SO2 sampling at volcanoes, it's also a mapping missions, and particularly about LST. Why do we care about LST? Because it's a key variable to detect evapotranspiration, because you see evapotranspiration is a function of heat, ground heat, and land surface temperature. Obviously, there are a variety of inversion algorithms that NASA developed. The main one used on board EcoStress is a temperature emissivity separation. It's quite complex. It can't be really carried out on board, but with HyTI and the ALTA algorithm, we're trying to do level 1 to level 2 on board for LST. The performance of the ALTA inversion, about 3 PLSR components can explain 88% of the variance. And again, remember, HyTI is 25 bands, so that would be about 100 floating point operations per pixels for HyTI. So totally doable on the Unibap, on the small Unibap onboard computer. So that's what we're trying to do. And here I want to show you some preliminary results that we did using simulated HyTI data. So we took some high-test scenes of California, of fields in California near Salton Sea. We downsampled the the high-test images to the same spectral and spatial resolution that HyTI will have. You can see here. We applied the retrieval to these HyTI simulated image scenes. And then we considered the NASA-derived LST maps from HyTest and downsampled them to HyTI spatial resolution. And then we carried out a simple difference. You see the difference between the two is plus or minus 2 or 3 degrees Kelvin. We did a similar thing for a variety of other scenes. Here you can see an examples of an urban scene. These are actually the roofs of the JPL lab in California. You can see even here, this is actually even better. The agreement is plus or minus 1 degrees Kelvin here. So some preliminary results. We also tried to look at carbon dioxide measurements at Kilauea volcanoes using HyTI, trying to use the hot lava lake as a background to isolate the volcanic carbon dioxide from the atmospheric one. Quite difficult to do it, but you see, assuming a plume temperature of about 2 degrees Celsius, we were able to discriminate. This is still very preliminary and work in progress, but I just wanted to show you this as a link to our next topic, the CO2 ranging for self-driving vehicles. Now, you see, this is it doesn't really this topic is not really about volcanoes, but I just wanted to mention it because it's the same physical problem. With volcanoes, we had a known distance between the camera and the plume, whether it's from space or from the ground. Here we have and a variable volcanic gas concentration. Here we have a fixed gas concentration, that's the carbon dioxide because it's relatively well mixed in the atmosphere, but we have a variable distance. So it's the same physical problems, just flipped. Here we're trying to use the mid-wave infrared for 4.5 microns. There is a nice CO2 band centered at 4.3. This is a large project with, there's us, University of Hawaii. I am the PI for this project. There is a Spectrum Photonics, which is a company here in Hawaii, which is specialized on building hyperspectral imaging systems. And then there's Kitware on the mainland in Virginia. So it's a big collaboration. So we're gonna plan on installing a variety of LiDAR and stereo vision systems on the self-driving vehicles, but the carbon dioxide will be a part of it. And here you can see a cartoon. We carried out the same ALTA inversion for carbon dioxide, but instead of retrieving the concentration, we're trying to do the range. And here you can see the expected errors. So over range for different thermal contrast between the temperature of the atmosphere and the temperature of the particular target, you can see for delta T of 1 degree Celsius at 20 meters, we're about 12% error. So this is still in progress, but I just wanted to give you some hints about what we're doing here. Now I want to talk about detecting hotspots. Now, many of you are familiar with the ModVolc algorithm developed by Rob Wright here at the University of Hawaii. About 10 years ago, it uses infrared satellite data acquired by MODIS to monitor the Earth's surface for hotspots. Now, ModVolc does a very good job in detecting very high temperature events, such as, for example, lava fountains or lava lake, which you can see in this recent picture that I took at the summit of Kilauea. And the algorithm, the algorithm works basically by considering the 4 microns and the 12 microns band MODIS, and by defining these NTI, there is an equation here. NTI is we call it the normalized thermal index. Basically, it's an empirical formula. If this NTI exceeds -0.8, then the pixel is considered a hotspot. As I was saying, this algorithm does a good job at getting high thermal energy hotspots, not so much with low emissivity. But volcanologists are very interested in the low emissivity detection of hotspots because those are the kind of unrest that precedes volcanic eruptions. So for my postdoc, I work with a couple of other guys here at UH, mostly Harold Garbiel, Eric Bilger, and Rob himself, to try and improve this algorithm. And first of all, we came out with an idea. Would a simple mean and standard deviation method work? So basically, calculating mean and standard deviation for basically 10 years worth of MODIS data, and then if basically the 4 and 12 micron spans would exceed the standard deviation for 10 years worth of data, is that a hotspot? Well, we tried this approach. You can see the big island here. Works quite well for Kilauea. You can kind of see, this is the NTI. You can see the hotspots detected by NTI. Using 3 standard deviation excess, that's pretty good job here. But it has serious problems in areas such as, for example, Iceland, you can see here, or New Guinea, areas that are occasionally affected by ice or high and low altitude clouds. We get lots of, so you see NTI, not many false alerts. This new method, lots of false alerts here on the ice pack, so the floating ice just to the north west of Iceland, and lots of false alerts too, mostly related to low and high altitude clouds in New Guinea. So basically this new method we came out with does worse than NTI, as you can see here. So not a good improvement. So we came out with a different idea. What instead if we considered maximum radiance here? Well, we considered the 4 and accompanying 12 micron span for 8 years worth of data, large global map. And then we came out with this idea. We considered the maximum 4 micron radiance values and the accompanying 12 microns, obviously, for which the temperature difference between these 2 bands does not exceed this empirical threshold of 12 degrees. Okay. Now, will we be able to detect, high temperature events such as lava lakes or, explosions such as this Strombolian one, like HyTI, like the NTI method will be able to do better? Well, here are some preliminary, again, bear with me, preliminary results. This is Lascar volcano in Chile. NTI didn't detect any alert during the first 300 days of 2014, but there were some low temperature lava dome activity and extrusion and avalanches during 2014. Well, we call it the MAX method. The MAX method indeed detected 4 alerts. This is the kind of low thermal emission activity that volcanologists are very interested in. This is just a plot showing MAX minus NTI. We also consider Shivaluk volcano in Russia. Again, NTI, the ModVolc algorithm, began to detect activity in March. There was an eruption here, but with the MAX algorithm, we were able to detect low temperature pre-eruptive activity events. Pre-eruptive activity events 2 months before ModVolc began to detect data. I'm showing you just 2 examples, but we computed we are computing about 150 volcanoes on Earth during 2014. We are also monitoring some wildlife in California and Oregon during the summer. And so based on preliminary results, ModVolc, so the MAX method detects on average 50 to 100% more alerts than the existing ModVolc method. This is some, some results, some preliminary results again that I am, sharing with you. This is mostly my postdoc work here. And now now we are at the proposed work. Okay, so revealing transitions in volcanic activity from space. What we want to do, this is a project that I'd like to carry out with Florian and Matt at NASA Ames. The goal of this project is to basically better understand how changes in volcanic gas signals transitions from unrest, dormancy to unrest to volcanic eruptions, and how and when these detections for mostly sulfur dioxide and specifically carbon dioxide can be detected from space. As mentioned to you, carbon dioxide would be better for volcanologists because it can, it yields information about magma dynamics at depth as opposed to SO2. SO2 is easier, carbon dioxide is more difficult, but it would be more useful. So what we proposed to do is basically to use NASA's OCO3 data, because we have so OCO2 data. With OCO2 data, we were able to detect carbon dioxide at certain volcanoes, particularly Yasur here in the South Pacific. But surprisingly, not much of the OCO3 data have been looked at yet. So that's why we're kind of interested to see if we can see these transitions in activity from space. And there are there are so many volcanoes active. On average, here we have about 10 years worth of data, and on average there are 30 to 40 eruptive cycles active on Earth in any given week. So there is really a lot of data to potentially look at and to learn more about how volcanoes degasses and how we can learn more about these transitions. Also, we would like to use GOSAT data to complete to complete the OCO3 data. And specifically, we would like to develop an SO2 gas retrieval algorithm specifically for GOSAT to look at these volcanoes. And so this is basically, here this is a map taken from one of Florian's paper where we can see the database that we have for all these active volcanoes on Earth, where OCO3 basically looked at. And so this is basically the idea of, and now obviously here I don't have any data yet, but we hope to build on our expertise and to investigate these transitions in activity from space. So just to wrap up this talk, I gave you an overview of the HyTI mission, what we're trying to do to process data from raw data to level 1 and level 2 onboard. This is obviously still in progress. We don't have any data yet. Hopefully the mission will be launched in 2022. But it builds on expertise that we had from the thermal hyperspectral imager sensor, which remember was a ground-based sensor. We're also trying to use carbon dioxide to determine inter-vehicle range for self-driving cars. This is mostly forgot to mention before, it's a DARPA-funded project. We detected a low-intensity volcanic thermal emissions from MODIS data, and then we have our OCO3 and GOSAT project, which is the proposed one. So this is I hope I gave you an overview of what I'm working on. I hope to work on. Obviously, this was very brief, so I hope I covered most of it. But I am very happy to take any questions that you may have. I want to finish with this picture I took a while ago in 2011. This is Stromboli volcano erupting at night. That's, I think, the end. Thank you very much for your attention.